Started?
Yes.
Okay, great. So let's begin. So it's a great pleasure to have Dongmin Gang, who's joining us from Seoul, where I think it's 11 p.m. at this point. So thanks for agreeing to do this so late. And he'll talk about IR phases of 3D class R theories. So please take it away. And everyone, please ask questions as always in the seminars.
Yeah, thank you for the introduction and thank you for invitation and thank you for coming to my talk. So I'm Dongmin Gang from Seoul National University. Today I'm going to talk about IR pages of 3D class R series, which is work in progress with Hichul Kim and Sunjin Che. And let me start. So as you may know very well, extra dimensions and the compactifications are very common idea in string and M series. A typical problem is determining the physics of the low dimensional series from the mathematical structures or geometrical structure of the internal space. And in this perspective, 3D series correspondence provide the ideal setup for these problems. So 3D correspondence studied the 60 series compactified on 3 manifold. And on 3 manifold side, and this is very well studied by mathematicians, and this has very rich geometrical structures, and this is well studied. And there is a kind of some classifications which I will review this talk. And on the other hand, in physics side, and 2+1 dimensional field series is very interesting. It has very rich IR dynamics, and there are some topological Chern-Simons terms, and there is could be some non-perturbative monoperturbers, now no-correlated called monoperturbers, and there are lots of the IR dualities. So this is a very interesting topics in physics, and we also have very strong tools to study this kind of series using the so-called supersymmetric localization. So in that sense, the 3D correspondence setup provide this very ideal setup for studying these problems. So this is the outline of my talk. So first, I will explain the exceptional dampings and in class R series. So this is the main some mathematical concept. So I will review this exceptional damping from the beginning, from the basic things, and then how this exceptional damping is realized in the 3D correspondence. Then I will give some mathematical review on the classification of the closed 3D manifold. Then I will give how to determine this IR page of the corresponding class R theory according to these classifications. And let me conclude and let me comment by giving some future directions. And please feel free to interrupt me when you have any questions. So let me explain what is the exceptional damping. So let me start very beginning. So let me first explain what is the damping. So in this paper, we are considering N is always denoted as some 3 manifold with a torus boundary, which is also hyperbolic. Hyperbolic means that we can give some this kind of uniformly negatively curved metric on this manifold, and so N has a torus boundaries. So it's a very bad drawing, but this 3 manifold it can be roughly given in this form. So this is a bulk, and this is boundary torus. And I denoted the boundary torus one cycles as basis as A and B, and the general boundary one cycle element can be realized in the linear combination of the A and B cycles. And here PQ are the integers, and along this boundary, this metric is roughly given in this form. And this theta1 and to parameterize this torus at the infinity. And this in 2D analogy, this maybe can be regarded as a Riemann surface with some holes or punctures, Riemann surface with the punctures. And these punctures can be regarded as some boundary with the S1. And so this is a 2D analogy. And Dehn filling procedure is a very well-known procedure. So from the starting from this one cusp of 3 manifold with a hyperbolic 3 manifold with a torus boundary with some closed manifold without any boundaries. So this procedure can be given, and this is given, and this I will denote this closed 3 manifold obtained by Dehn filling of this N with a slope PQ. This slope is in this way NPNQP. So this notation says that we are considering the gluing of this hyperbolic 3 manifold with the torus boundary with the solid torus, and we are gluing this some boundary one cycles, which is primitive boundary one cycle, which is labeled by choice by P and Q, where P and Q are now co-primes, and we are gluing this chosen one cycle to this Schrödinger cycle of this solid torus. Then the resulting topology depends on this choice of the P and Q, and then the resulting manifold does not have any torus boundary. It becomes a closed 3 manifold, and this closed manifold are denoted by in this notation. So please remember this notation. And this is Dehn filling procedures. And in 2D analogy, so this is somehow is analogous to the closing functors on Riemann surface. So we consider some Riemann surface with the punctures, and we are closing this puncture with by gluing the disk. Then we obtain the closed Riemann surfaces. One crucial difference is that in 3 manifold cases, there's several options in the closing procedures labeled by and the PAQ, and in these cases there's no choices, and there's only one choices of gluing this procedure. So we have more choices, and in this way we can construct some infinity many family of the closed manifold starting from the one single 3 manifold with a torus boundary. In my talk, N always denotes some 3 manifold with which is hyperbolic and the torus boundary. Then what is the exceptional Dehn filling? And there's a very famous mathematical theorem which is called the Thurston's hyperbolic Dehn surgery theorems, which said that except for the finite many PQs, and the resulting closed manifold is always hyperbolic. So if we start from the hyperbolic and we do the Dehn filling along the P and Q cycles, and this is always hyperbolic except only finite many cases of choice of P and Q. And this choice of P and Qs are exceptional Dehn filling. So exceptional Dehn filling give the manifold which is non-hyperbolic. So we start from the hyperbolic manifold, then after the exceptional Dehn filling, and this becomes the non-hyperbolic. So this is called exceptional Dehn filling. So non-exceptional Dehn filling means that when this resulting closed manifold is hyperbolic cases, we call it non-exceptional. But the resulting manifold non-hyperbolic, then we call it is exceptional Dehn filling. So this exceptional Dehn filling is very interesting because that yeah, please.
So what about you start with non-hyperbolic manifold, for example, three sphere?
And the resulting, then always the non-hyperbolic. If you start from non-hyperbolic, then the resulting manifold after the Dehn filling is always non-hyperbolic.
Okay.
Okay. So to construct the hyperbolic closed manifold from Dehn filling, we should start from the hyperbolic 3 manifold with the torus boundaries. Yeah. So thank you for the questions. So why this exceptional Dehn filling is interesting in mathematical perspective is that so according to the Thurston, so 3 manifold can have some geometric structure which is called H geometries, and the hyperbolic manifold of course corresponds to one geometric structure called the hyperbolic structure, hyperbolic geometry, and the non-hyperbolic manifold can have other 7 geometries. So this exceptional damping describes some drastic change of the geometric structure on the so it corresponds to the drastic change of this geometric structure of the three manifolds. So it is more interesting than the non-exceptional damping, which is just mapped to hyperbolic geometry to another hyperbolic geometry. So in this respect, so this is exceptional damping is more interesting than the non-exceptional damping. Then let me explain what is the 3D counterpart of this damping. So class R series is schematically defined in this way. So we start from the 60 so-called 2,0 series, which is a 60 series, which has a maximal supersymmetry. And we compactified on this 6 series on the three manifold M. I already know this is closed three manifold. So M. Then we do to preserve supersymmetry. So we do some partial topological twisting using the R symmetry. So 60 series, this year 60 series has SO5 R symmetry, and we are considering some SO3 subgroup to use, and we will use this subgroup to do the topological twisting. Then we are considering the limit when the size of the three manifold is very small. Then we will expect that we will get some 3D theory, which is labeled by the M. So, and actually it is only depends on topological structures of the M three manifold and at the low energy. So this will be denoted by TM theory on the 3D theory. So in this way, we can geometrically engineer the 3D theory labeled by this three manifold M. So after this topological twisting preserve the cut supersymmetry, the cut of the supercharge, and the resulting theory preserve the four supercharges and generically, and it become the 3D n equal 2 superconformal 3D n equal 2 gauge series. And the remaining U1 R symmetry this the SO2 R symmetry of the SO5 out of the SO5 R symmetry in 60 become the U1 R symmetry. And I will call this the U1 R symmetry of the originated from the 60 R symmetry by the U1 R geometric symmetry. And there could be another R symmetry by mixing with some U1 flavor symmetry in the field theory, but there is some special U1 R symmetry choices, which I will call the U1 R geometry. So then this says that this three manifold, which is obtained by this damping operation, especially we are considering that then the Q equal one cases, it is called the integer damping. So which is only labeled the P. In this case, it turns out that this damping corresponds to in 3D theory corresponds to some gauging of the flavor symmetry. So 3D theory associates some 3D manifold with a torus boundary, and this theory will be denoted by T, A, and B. And actually, it depends on not only the choice of the 3D manifold, but also depend on choice of the boundary one cycles called A and B. And in this theory has known to have some SU2 flavor symmetry, and it is 3D manifold cases with torus boundary cases. This theory has SU2 flavor symmetry. Then this damping corresponds to this gauging of this SU2 flavor symmetry. And there is very subtle some structures, some structures. So we should be careful in the gauging this symmetry, depending on whether P is odd, even, or odd cases. But anyway, this is just a gauging, and I will call this as SO3 gaugings. Correspondence, so we can say that this damping part corresponds to this gauging procedures of flavor symmetry. And this TNAB is a 3D theory associated with this N, which is a 3 manifold with the torus boundaries. And these are well studied by these papers. And this this theory is based on the ideal triangulation of this n, some hyperbolic, some cost hyperbolic 3 manifold. And there are some technical assumption we need to guarantee that this has SU2 symmetry, and yeah, you don't need to worry about these conditions. So this is some 3D counter-Weber damping procedures, and there is one which should be one Kepler, and the TM theory considered here is sometimes called the T irreducible theory, T irreducible M theory, and which is actually different from the some another TM theory, which is sometimes called T pure theory in the literature studied by these people. One crucial difference is that in our theory, TM theories, in my talk, so this theory is only see the some irreducible plot connection only see as the beta vector, and this theory, T pure theory, see all the SL2 plot connection as beta vector. So this is one crucial difference. So in a sense that this our TM theory considered here is somehow some subsector of this T pure theories, which is on certain subsector of the vacuum. But to me, so honestly, so I don't know exactly the precise relation between these two theories. And even the T pure cases, some very little is known about T pure theory for associated hyperbolic n. So even we don't know exist, we even not sure whether there should exist a single 3D theory which is all the SL2 plot connections. Yeah, so this is some comment, but in our cases, I will only consider this TM theory, which is sometimes called T irreducible theories. So this is different from the T pure theories studied by these people.
So can I ask what you mean with this last comment? The existence of a single 3D theory which sees all.
Yeah, so we are not sure whether single 3D theory should see there should exist some single 3D theory which is see all the plot connection as a vector of R2 times S1.
Isn't that T4?
Yeah, so some case, yeah, some non-hyperbolic cases, people found that some field theory description, so which represents all the.
But you're saying for the hyperbolic case.
Yeah, hyperbolic cases, yeah. So we are not sure whether there should exist, and so yeah.
And how do I see the difference from the compactification?
Yeah, that's other. Yeah, we that I don't know exactly. Yeah, so we somehow we do some procedure. So in the taking some limit, and there could be some, if there is some disconnected branch of the vector, then maybe we need to choose some certain branch in the compactification. And I think that our TM theory, we are choosing some certain branches in the compactification. Yeah, but yeah, we try to give some physical interpretation of this T irreducible theory in my paper with Kazuya. Yeah, but yeah, so it's very tricky. Yeah, so yeah, frankly, yeah, speaking, so I'm I still fully understand. Yeah.
Okay.
So anyway, so our TM theory has a well-defined field theory description. If you forget about the 60 pictures, there is a very well-known procedure to construct the theory for given 3 manifold. Yeah. So yeah, you can forget about 60 picture, but we can just say that this TM here is some 3D theory labeled by 3 manifold, depending on the topology. And we expect that this is somehow related by 60 theory compacted by on the 3 manifold, but the precise 60 definition is not, very, very subtle, tricky issues. But anyway, this has a well-defined field description, and for given 3 manifold, and we can give a field description. And it only depends on the topology, and 3 manifold can be represented in the different ways, and different representation gives different field theory description. But it turns out that all the different descriptions are related by the dualities. So it only depends on IR physics, at least it's IR physics, it only depends on the three manifold itself. So in summary, so in class R series, the damping corresponds to gauging, and this slope P is given by the gauging Chern-Simons level of this gauging procedures. So for spin shuttle large P, so in Chern-Simons theory, P 1 over P is inverse corresponds to coupling constant in Chern-Simons theory. So if P is very large, then this corresponds to weakly coupled series. And we know that according to the Thurston's theorem, then we know that this should be hyperbolic. If it's sufficiently large P, and this is hyperbolic. And then we expect that there's nothing interesting, surprising happen during the gauging, because that in the geometric size, this just becomes the hyperbolic manifold, become another hyperbolic manifold, and we don't expect nothing interesting, surprising. And it turns out to be true that nothing interesting happens. And this is also expected from the field theory point, because this is correspond to weakly coupling theories, and nothing interesting will happen. So for example, T and PB for these cases, it's just just n equal to CFTs, which is this CFT is very similar to this CFT associated with n, and in the sense that his center charge of this series after gauging is very similar to this center charge, stress and center charge before the gauging. So this is so in a sense is a boring cases. And for small p cases, it corresponds to strong coupling in gauging, and the geometrically, this could be the non-hyperbolic, and the small p cases, we expect that there are various non-perturbative effects become important, and such as the light monopole operator appears, and so in this case we expect the various IR pages. Supersymmetry, some cases supersymmetry is spontaneously broken, and supersymmetry can be enhanced, or some cases it has a mass generation and can emerge. So we expect that in the field shear aspect, when we expect the very interesting IR behavior will happen when P is very small, and it actually corresponds to when this damped manifold is non-hyperbolic cases. So let me give a very concrete examples. So so this is some three manifold with a torus boundary, which is called the peak knot complement, and this is determined by the choice of a knot, and we choose some so-called pivot knot, and this is some kind of a knot, and I forgot to draw this knot diagram, and this is some knot with the pivot crossings. And so we are considering knot complement, and this is obtained by three sphere removing the tubular nave of this knot. Then we obtain the three manifold with the torus boundary, and then we will do some dampings with labeled by P and Q series. Then the resulting series is turned out to be given by in this form. So this is a gauge theory with the U1 times SO3 gauge group with the Chern-Simons level is -half, and this is a P -4. And this P is the same as this P, coupled to chiral field in the adjoint representation of SO3 and the charge 1 on. And please believe me that nowadays we have various way to check this IR dynamics, and then we found this conclusion. For figure 1 and 2 and 3 cases, surprisingly, we found that this theory is pro to the n equals 4 CFTs. There is a SUSY enhancement, and this theory only manifests as n equals 2 theories in 3D, but we found that this has a SUSY enhancement in these cases, and the pro to the n equals 4 CFT. And more interestingly, this n equals 4 CFT is actually the length 0. Length 0 means that there is no Coulomb or Higgs branches. Actually, there is no non-trivial vacuum moduli space. So this is very simple n equals 4 CFT, but it's non-trivial n equals 4 CFTs in these cases. And the P equals 0 and 4 cases, and it turns out that we are doing the gauging of the SO3 flavor symmetry, then there is also associated monopole operators, and these monopole operators are usually not gauge invariant, and it should be addressed by the method field, and then after method field, then this monopole operator can be so gauge invariant. But in this procedure, this monopole operator usually become the quarter BPS operators. But in this P and P equal 0 and 4 cases, it becomes this monopole operators, gauge invariant monopole operator actually becomes half BPS monopole operators. And so this only happened the P equal 0 and 4 cases. And the other cases, we found that there's nothing interesting. And the field shear analysis is a very nice, good, nice match with that the well-known non-mathematical fact that for these cases, P equal 0 to the 4 cases, this corresponds to non-hyperbolic manifold, and otherwise this corresponds to hyperbolic manifold. So from this experience, we found that for these hyperbolic cases, the correspondence relative theory is just nothing interesting happening, and for non-hyperbolic cases, so very special things happening, and the IR dynamics is very non-trivial. And this is one example. And then let me give a more interesting examples.
I have a question.
Yeah, please.
Yeah, thanks. In the previous example, do we also see some distinction between P equals 1 to 3 and P equals 0?
Yeah, that's yeah, exactly what I'm going to talk about. Yeah. So these are correspond to non-hyperbolic manifold, and the non-hyperbolic manifolds can be further divided into several different classes, and these two cases correspond to different classes. Yeah. So this is why they see the different IR behaviors. Yeah. That's the main thing I want to claim. Yeah. Yeah. Thank you for the questions. Yeah.
Is there a physical understanding behind this? For example,
that's also what. That's also what I'm going to talk about. But we still But as I told you, we don't have the full understanding. But we did many experiments, and then we can confirm that we find some rules and try to understand from the 6D picture, and we give some partial answers, partial explanation. But there are lots of the subtleties. Yeah, cool. As I pray. So let me give a more interesting example. So this is so-called M006 manifold. This is a 3 manifold with a torus boundary, hyperbolic, and this is some mathematicians' notation. Mathematicians try to give all the list of the 3 manifold, hyperbolic 3 manifold with torus boundary, and they labeled by M003, M004, something like that. And this is some M006 manifold, and we are doing the damping along some choice of the cycles, and the corresponding solidity theory we can easily construct it, and this theory is become the U1 times U1 gauge theory with coupled solid chiral with the charge is given by this one and with the spot potential. And the one non-trivial thing is that this theory is have a U1 times U1 symmetry associated with this U1 topological symmetry. But it actually this will U1 times U1 topological symmetry will enhance to the one of them linear combination enhance to the SO3 flavor symmetry at IR, and we are gauging this SO3 flavor symmetry at IR series. So in a sense, this theory does not have any weakly coupled Lagrangian description, but this is have some definition. So this theory in the numerators has a symmetry enhancement at the IR, which have SO3 symmetry enhancement, and then we are gauging this enhanced symmetry with the Chern-Simons level. So this theory corresponds in constructed in this way, and again we can do the similar analysis using various techniques, and then we found that the P equal -2 cases, then there is a supersymmetry enhancement, and it becomes a n equal 4 CFT over length 0, and the P equal -3 cases, and this monopole operator of S3 becomes the half BPS instead of quarter BPS, and the P equal 1 and -1 cases, and there is a mass gap, and it flows to the unitary topological series, and the P equal 0 cases, SUSY is spontaneously broken, and the other cases, nothing interesting happened. It just become some some SCFTs. And this is also a very nice agreement that the mathematical fact that this M006 damping cases, for these cases, this is a non-hyperbolic, and other cases, this is hyperbolic. So main goal of my talk is that determine the IR page of this series for non-hyperbolic M, which correspond to exceptional damping from the topological property of this non-hyperbolic manifold M. So this is a main thing of that. When this manifold is hyperbolic cases, it just flow to always some SCFTs without nothing interesting happens. So in my talk, I mostly focus on the hyperbolic, non-hyperbolic cases, because hyperbolic cases, we know that what will be the IR pace. It's just a SCFT. There's no mass gap, and this flow to the SCFT. There's no SUSY enhancement or no SUSY spontaneous broken, and just flow to the supersymmetry n equal to SCFTs for hyperbolic cases. So strategy is just doing some various experiments. So in this way, so we have some changing this M006 to M007 and M008, something like that. And then we studied all the IR pace for corresponding to the non-hyperbolic exceptional damping. Then we tried, and then we try to find some patterns, and then we want to give some theory for this theory, and then we want to give some interpretation using M theory. This is our strategy. And for the experiment, so first we used some mathematical program called the Snappy, and then it will give us some ideal triangulation of this M003 and M004 and something like that. And then using some algorithm proposed by Dimov group, we can construct field theory construction using this ideal triangulation. Then we can compute the various supersymmetric parting function using localization. Then from this supersymmetric parting function, we determine the IR pace. Then we compared with the topological type of this one. In this way, we did lots of the experiment, and then try to understand some general rule, and then try to understand from the M series pictures. And this is Snappy, and so if you type this manifold, then they give some glue equation for the ideal triangulation, and using this one, we can explicitly construct the field series. And then there's also very nice paper by mathematician, and they all studied by this exceptional damping, and they studied this number, huge number of these n cases, and they classified all the exceptional damping, and they also give what is the resulting three manifold after exceptional damping. So for example, if we do the exceptional damping for M003 from this coefficient, then we get this kind of manifold, and in this case we get this kind of manifold. So using this Snappy and this mathematical program, then we can do this kinds of experiments. So this is okay, and then let me give the final answer we found. So in these cases, in this IR page class R theory can have this kind of pages. So some cases, nothing interesting happens, and it always corresponds to hyperbolic cases. And this is some classification of a three manifold, non-hyperbolic three manifold, hyperbolic and non-hyperbolic three manifold, and I will explain it later. And this is a hyperbolic piece, and the others are the non-hyperbolic parts. And this is a criterion of this classification, and I will explain that in details. And then this manifold can be divided by in these classes, and I will 5 classes, and I will call that is finite and complex, and it always corresponds to hyperbolic cases, and then or some cases the infinite classes, and there's also unitary and non-unitary classes, and these are class of the non-hyperbolic manifold, and then these are some resulting IR pace. For hyperbolic cases, nothing interesting happens, and for this class, for length space cases, it is a supersymmetry broken pace, and this infinite type class, and this is infinite type class. We found that this has some half-base monopole operators coming from these monopole operators. And this yellow type, I will call this as a finite real cases. This corresponds to TQFTs. And this classes, this orange, and this corresponds to finite real and the non-real type. Then this class corresponds to SUSY enhancement and the flow to the N=4 rank 0 SCFTs. And there's some another classes manifold, and we need more studies. Yeah, this is a summary of my so our project. So yeah.
So I'm a little surprised that this need more studies thing, it doesn't extend to graph manifolds, because I thought the graph manifolds are actually much more complicated in general than just ciphered fiber.
Graph manifold, graph manifold. So has a very graph manifold covers that all these pieces, and it contains some ciphered fiber and this one, and there's a lot of the other type of manifold, and for that classes we haven't studied much, and we need further study. Yeah, so graph manifold is very huge class of non-hyperbolic manifold, and so we only studied. Sorry.
For all of these, you know, there's this half EPS monopole operator.
This one. So infinite type, and the graph manifold. Some of graph manifold contains the other types also. Graph manifold contains all this one. All this one.
I thought graph manifold was even larger than just, you know, ciphered fibered. And
of course. So the graph manifold, so I will
there's
explain
really
this
something extends out. You have general graph, and you have to sort of you fiber over a generic graph, and the plane can have loops.
So that class is correspond to this one. This mysterious part. Need more studies. Okay. So actually this part is very large, but I draw it a very small portion, but actually it is very big portion. Actually, this hyperbolic piece is much bigger than the non-hyperbolic piece. But this piece is also very large, and we need more studies, and we still don't know exactly what is going on.
What is that case? I'm going to explain what is that case that needs more studies. Are you going to explain what is that case that needs more studies, like that rainbow?
So in this cases, we couldn't. So the problem is that in these classes we couldn't find the field theory description, because we can find it, but the field theory description is so difficult. So we need too many ideal tetrahedron to construct this theory. So it means that we need too many chiral multiplets. So so analyzing this theory is very difficult for us. We need to do some integration, a lot of integration, large integration, path integral, the localized integral, and we couldn't perform the analytically, we couldn't do it. So this is why this part is.
No, I meant what kind of ciphered manifold are they?
This manifold.
This part.
Manifold, so I will explain later.
Okay. Another question. I thought the DGG construction was only for hyperbolic manifolds.
So this construction is only three manifold with the torus boundary. So this construction gives this part, numerator part.
Okay.
And then we can do the damping procedures.
I see.
Then we could get some non-hyperbolic manifold starting from the hyperbolic end.
I see. Okay.
Actually, this construction also can be extended to the non-hyperbolic three manifold with the torus boundaries also.
Okay.
They construction only need some ideal triangulation, and we can also do some ideal triangulation of this three manifold with torus boundary. And in this paper, they actually give some example which correspond to track point knot complement, which is not hyperbolic. But our starting point is that hyperbolic n, and doing exceptional damping, because that I think that studying this page is more interesting. Starting from the SCFT to get some other pages is more interesting.
So I have to ask again. So you're looking at these particular NPA plus B. So you said this Q equals to 1.
Yeah.
And that covers this whole picture, or this is a subset of this picture? Once you.
Yeah, that's a good question. So, yeah. So there is a very famous mathematical theorem says that every 3 manifold can be obtained by some link with the integer damping. So, but for that we need to start from the link with the several components of the torus. But in our cases, we are only focusing on this N with a single torus.
Yeah.
Then actually this cannot cover all the 3 manifolds actually. So yeah, so to complete our story, then we need to start from the link complement and do this kind of gauging several components of Dehn, and we should do that. But in our paper, we just focus on this single component.
Okay, so it's basically cutting through a subset of this graph on the right.
Yeah. So I think that this part maybe some of these mysterious parts cannot be realized from this cases. Yeah. So the mathematical paper I mentioned, yeah, here in these papers studied only the single component of that, and then they give this kind of manifold, and it does not cover all the manifolds, all the 3 manifolds, and yeah. So to extend our work to the general link and the damping, then we need another mathematician's work studying this kind of thing. Yeah, we cannot do it, so we stopped. Yeah. So this part, yeah, maybe correspond to that one. Yeah. So yeah, so this is basically the conclusion of my talk. But let me give some technical supplement of my talk. So maybe I hope so it does not take much, but the last part of my talk will be very technical. But this is the main message of my talk. So let me briefly give some mathematical, not briefly, but some classification of a 3 manifold. And one very famous classification scheme is whether these 3 manifolds have an essential sphere or torus. I will explain what is essential sphere and torus. And according to this, depending on this existence, and the 3 manifolds can be divided 4 parts. One is this part. The horizontal line is depending on whether there's no essential sphere and there exists. For there exists essential sphere, we call this as reducible. And if there is no essential sphere, then we call it irreducible. This is because that if there is the essential sphere, we can cut the 3 manifold into 2 pieces, and then the 3 manifold can be obtained by gluing the 2 manifold. So in this sense, that this is reducible, and if there is no essential sphere, then this is irreducible. And similarly, we can divide by 3 manifold into toroidal and atoroidal, depending on whether this manifold has a toroidal torus, essential torus, or non-essential. So in this one, but in my talk, I will mostly focus on this irreducible cases, because the reducible one can be constructed by gluing some, in a sense, the connect some of this irreducible piece. So mostly I will focus on this irreducible piece. And then let me explain what is the essential spheres. So is a sphere. So essential sphere is a sphere that does not bound the 3 ball. So in 2D analogy, and this is the essential spheres S1, and this is not the essential S1. It does not bound the 2 ball. So in a sense, this is these are essential spheres. So and then the mathematicians studied that the further classification of this irreducible piece, and the irreducible piece can be divided in 2 parts, which is the toroidal and atoroidal. And among the atoroidal, there's a very famous class, which is called the hyperbolic cases. And this is mostly hyperbolic cases. And there's also some non-hyperbolic atoroidal manifolds, and also one. And among these non-hyperbolic cases, and the people also divide into the two classes depending on whether this has this three-manifold contains the hyperbolic piece in the JSG decomposition. JSG decomposition is roughly the toroidal decomposition, and we decompose if there is an essential torus, and we divide the three-manifold into the two pieces using along this cut torus. Then if one of in this decomposition, if one of this component has a hyperbolic, then we will call this a hyperbolic piece, and otherwise, then they will call the non-hyperbolic case. Is a graph manifold. So this graph manifold covers the very large class of the non-hyperbolic three manifold. So non-hyperbolic three manifold can be divided into two classes: hyperbolic piece in JSJ decomposition, and in the other cases, which is called the graph manifold. And this graph manifold contain the various interesting subclass of three manifold. And this is not all the graph manifold. There are another graph manifold. And there's one interesting class is so-called the Soul manifold, and another class is pivot spaces. And the pivot space contains also the three pivot space, and also contain the length spaces. And the graph manifold and the other part of this one correspond to this mysterious part, which we haven't studied. Yeah, so we are missing lots of three manifold in this class. So yeah, we are only studying this subclass of the graph manifold, and other graph manifold we need further studies. And let me explain what is the Soul manifold and the pivot spaces. Soul manifold is basically torus bundle. Is a torus bundle of the S1 and with some monodromy matrix with SL2G satisfying these conditions. So this is a anosop map, and this will give a torus bundle. And this class of manifold are called the Soul manifold. And the three pivot space is labeled by three coprime numbers. And this has this kind of dense surgery description. And I will skip the more detailed description of this three manifold. Anyway, this three manifold labeled the three pieces of coprime numbers, and this has a nice dense surgery representation using this type picture. And this LPQ is a length spaces, and in dense surgery description can be regarded as this one. And this is some graph manifold we will study in this talk, and there's other class of graph manifold. There's a bunch of the huge class of the other graph manifold. We still need to further study it, but I won't talk about that manifold. Yeah, but so yes, so mathematicians classification is based on the existence of essential sphere or existence of essential torus, but it turns out that I don't know exactly, but for our purpose, it is more important than the existence of separating essential surfaces. Yeah, it is more relevant criterion to determine the IR page, it turns out to be. So let me explain what is the essential sphere and what is separating and non-separating. So in the 2D analogy, this is the essential sphere I told you, and this is not essential. Among the essential sphere also can be divided two classes. One is non-separating essential sphere, and this is a separating essential spheres. And for our purpose, the existence of separating essential spheres is more relevant to our determining the IR pace. I don't know exactly why, but it turns out to be that the existence of separating essential sphere is more important. So if there is an essential separating essential sphere, then we can divide by three manifold in two pieces, and the three manifold can be given by the gluing of two three manifold using so-called connected sum manifold. Yeah. So this is a essential, and similar we can define the essential separating essential torus, something like that. So for example, that S2 times S1 is a three manifold which has the essential sphere, but which is not non-separating. So if it is an essential sphere, but if we cannot cut, then this does not divide into three pieces, two manifold, but it give just one. So this is an essential sphere which is non-separating, and this torus bundle is also the example that the three manifold which is has an essential torus, but it does not non-separating. So it's not separating. So separating. So for the other example is something like a Riemann surface times genus 2 Riemann surface times S1 cases. There is separating essential torus because we can cut this one, then we can divide the three manifold into two pieces. So this is an example of the essential separating essential spheres. So this is the usual mathematician's classification depending on the existence of essential sphere and torus. But for our purpose, the more relevant thing is that existence of a separating essential sphere and torus. So we divide by three manifold in these classes. So this is a three manifold without any separating essential sphere cases. So for these cases, remember that this class corresponds to some atoroidal, and there's no sphere and no torus. So this class of course corresponds to this class because even there's no essential surface, so it means that there is no separating essential sphere. But the sum of the three manifold which does have a torus boundaries turns out to be the torus essential torus turns out to be the non-separating. Then in our classification, these are regarded as this yellow line. So, and the other part are called having separating essential sphere cases. And these cases. So all these pieces, hyperbolic pieces in JSG decomposition and the graph manifold, this type graph manifold, and these are all the reducible manifold except this S2 times S1. It turns out to have the essential sphere or essential torus, and then we divide by in this classification. So let me see that what is the implication of this.
Dongmin?
Yeah.
Can you say it again? What is that that colored that rainbow colored piece?
This one.
Yeah.
This one is that in these cases, this is this color cases that so this color cases that we are considering some graph manifold, and we are considering this kind of graph manifold, and there's another the other class of the graph manifold.
It's a separate manifold with three fibers.
Three fiber is the
I think it's everything that's not three fiber.
Yeah, everything
So
not
like four
in this
fiber
class is represented by this manifold. This manifold, yeah.
Oh.
So three fiber one corresponds to this yellow.
What I don't understand is what is this other gray bit? That's the thing that puzzles me more. But
Sorry.
There's something I don't understand about the graph, which is you have a ciphered fibered space, which is the red box. Okay, there are the length spaces, the three fibered with a sphere. And then you have more generally ciphered fibered spaces. That's the red box. So, but in your picture, you have a piece that you say you have to study further, but then there's a piece that's gray in the other picture, where it seems like you understand everything, but it's not in this class of three fibered guys either. So what is that gray piece in that cipher fibered box that is not in a rainbow color?
Not in a rainbow color.
How do you distinguish this rainbow color from the rest of the separate fiber?
Yeah, so for example, this is one example in the gray colors. This is Riemann surface times S1, genus 2, and this is a 3-manifold with essential torus. This belong to the gray colors, something like that.
I see. So these are sort of degenerate types of cipher fibers.
Yeah. So yeah. So yeah. So yeah.
Mhm.
Yeah.
Okay.
So yeah. So yeah. Yeah.
Anyway,
Gray color
I think
is.
we can discuss it later. Let's move on because
Let's
we
move
need
on.
to get to some physics. So
Yeah. So let me give us some implication of 3D class R. So to understand this one, we need to introduce 3D index. So this is a 3-manifold invariant, which basically compute this superconformal index of this 3D series using this geometric R symmetry. And actually the series could have a more fugacity, but this 3D index does not see any fugacity, and this only see the Q. So this is a Q polynomial, finite, infinity Q power series generically, and this is a 3-manifold invariant. And this is count half BPS local operator in the 3D series. And in terms of 3D series, if we are considering the empty brane left on this separating essential surfaces, then this may correspond to some local operator, supersymmetric local operator, some special supersymmetric local operator in field series. And the one nice thing about this essential surface is that we can wind this essential surface arbitrary times, 1 times and 2 times, 7 times. So it means that these operators actually correspond to half of this chiral primal operators. And this R charge, geometric R charge of this local operator can be also purely determined by the Euler characteristics of this Riemann surfaces. For torus cases, this is 0, and the sphere cases, this is -2. So it implies that so if there is a separating essential spheres in the 3-manifold, and there exists this half vessel chiral primal operators with this R charge, geometric R charge given by these numbers. So it means that this index diverges because that this index, the arbitrary number of this one, this is always Q to the 0th power, and this is Q to the -1 powers. And then this will have the arbitrary winding numbers, then this will give the divergence 2 to the 1. So we expect that if there exists the separating essential torus or spheres inside M, then we expect that this 3D index, which actually counting the local operators of this 3D series, will diverge. And so we expect that if there is a separating essential sphere or torus, we expect that diverge. So we call this as infinite type because that this 3D index diverges. And if there's no essential sphere, then we will call this a finite type because it 3D index converts as a Q series. So in our TM theory obtained by this Green, so we expect that for this case, we expect that there could be additional U1 flavor symmetry. Otherwise, this index does not make sense. So this correct R symmetry at IR symmetry should be some linear combination of R geometric and this mixing parameter mixing with this additional U1 F symmetry. So in order that this O sigma has satisfied unitarity bound. So we expect that in this case there could be the additional U1 flavor symmetry, and then which is not visible in the library looking at the geometry. But we also expect that this half-fifth chiral primal operator should be charged under this U1 flavor symmetry. Otherwise, this cannot have this charge. And the only way to get this half-fifth operator after gauging is that it should come from the monopole operator in the gauging procedure. So we expect that this half-fifth chiral primal operator corresponds to monopole operator SO3 flavor gauge symmetry. So we expect that for this class of 3-manifold of infinite type, we expect that there is a half-fifth monopole operators which associate this SO3 gauging procedures. And so we call that this infinite type and the finite type. And when the cases, and then let me give some another argument that the 3D index also can be written as some SL2C Chern-Simons series, and this has a nice some factorization properties, and this holographic block, and this holographic block has some nice perturbative expansion in the some Q equal 1 limit. So I'll skip all details, but the final result is that final guess is that so for finite m, so it means that the index converges. We expect that if there is the low denoted some flat SL2C flat connection, and if every flat connection and the Chern-Simons level, Chern-Simons functional of this flat connection of imaginary part is non-zero, then this index in the Carter limit behaves exponential growing behavior. So if we expect that this is an infinite power series in the Q half. But when the 3 manifold, all the flat connection is imaginary part of Chern-Simons level is 0, then we expect that this index is not exponential growth pattern in this hard limit. Then we expect that this is a Q independent finite number in the Q equal 1 limit. Actually, it turns out to be these cases, this 3D index becomes just 1. So we further divide by this 3 manifold in the finite type of 3 manifold in the zebra classes when this 3 manifold is empty type. In these cases, there's no irreducible flat connection. Then the 3D index should be vanishes because that this summation range is 0. So we expect that for this empty cases, is 3D index is 0, and the point for finite real classes, we expect that this index becomes 1, Q independent of numbers, and the finite complex cases, we expect that this is infinite power series. So this is some way to understand. So we further divide by 3 manifold in the, so we have an infinite type, and then among finite type, we divide into the complex and the real and the empty type, depending on the structure of the flat connection moduli space of 3 manifold. So empty means if there's no irreducible flat connection, then we will call this empty type, and we will call this complex if the SL2C flat connections are complex in a sense that it's a complex. It's a Chern-Simons action has an imaginary part, and we will call this as a real when all the irreducible flat connection has a real in a sense that its Chern-Simons action is always real. So in these cases, we expect that for empty cases, we expect that this combined index becomes 0, and when this m equal finite and complex cases, this is infinite power series in the Q half, and this is m equal finite and real cases, we expect this is Q independent, and it actually becomes 1. So from this picture, we expect that this index becomes 0 is a signal that the SUSY is spontaneously broken when the m is empty cases, and in these cases, finite and complex cases, we expect that this is just a CFT. Nothing interesting happens if m is finite and complex. And when the Q equal, in these cases, 3D index becomes the Q independent, and this seems to be a signal that this theory actually flows to the TQFT. So actually, that in this paper, we studied that for this type of 3 manifold, for which it finite real cases, we can also actually construct a TQFT associated with 3 manifold for finite and real cases. So actually that for 3 manifold with this type, we can actually construct the TQFTs. But the one non-trivial thing is that for some cases, this TQFT turns out to be non-unitary. So then how to interpret these cases. So in our cases, we expect that this TM theory, when this resulting TQFT is a unitary cases, it actually becomes a West gap and the flow to the unitary TQFT. And when this TQFT is non-unitary, we expect that this is actually flow to the n equal 2 CFT with additional flavor symmetry. That this index is actually not the 1, but if we turn off this additional fugacity, then this index becomes 1. And this is the additional fugacity. And most recently, we found that there is some very nice correspondence between the n equal 4 length 0 CFT and the correspondence between the non-unitary TQFTs. So from the motivated by this previous work, then we conjecture that for this when the this resulting TQFT is a non-unitary, then we expect that this TM theory actually prove to the n equal 4 CFTs with the length 0. So this is our claim. So this is a so from this result, and we naturally divide the finite and real 3 manifold into 2 more additional classes, which is unitary and non-unitary, depending on whether this TQFTs are unitary and non-unitary. So let me give a concrete example of a finite real 3 manifold. This 3-5 of the Dihn manifold is unitary or is always finite real, and it turns out that these cases it is unitary, and these cases it is non-unitary. And the corresponder is always finite real and always unitary for every arbitrary knot. And the others, and we expect there is some example of finite real 3 manifold from these mysterious classes, but we haven't studied it yet. So this explained all the class of the 3 manifold in our criterion. Then we explained what is the resulting the topological phase. And we check that this expected topological phase using the various example, and there is no exceptions, and we found that it does work. And this is an example I showed in the first part of my talk. And then in this 5-2 cases, this is this case theory is this one. And as I told you, in this P equal 1, 2, 3 cases is a SUSY enhancement, and the P equal 0, 4 cases, there's a half-base kind of monopole operators, and then we found that this is otherwise. And in this P equal 1, 2, 3 cases, it corresponds to 3-5 of the spheres, as 3-5 of the type of the spheres, and these are all the non-unitary type. So this is explained why we have the n equal 4 CFTs. And this P equal 0 cases, this is an infinite type. And this is explained why we have half-base monopole operators. And otherwise, this is a hyperbolic, and the hyperbolic always corresponds to finite complex, and this corresponds to CFTs. And similarly, we can do the second example, and it nicely also work. And we also give more examples, and we found that there is no exceptions. And this is some conclusion of my talk, and there's some further direction, and let me stop here. Yeah, thank you for your attention.
Great, thanks very much for this nice talk. Other questions? We had already lots of questions, but let's see whether other people. So could you, in the slide that you just sort of skipped over, could we go back to that one? Right. So can you comment a little bit on how what is sort of the current status of this classification of 3D phases versus 3 manifolds, which I think you probably want to restrict to unitary, and so is this sort of proven at this point, or what's the current understanding that you have?
You mean that sorry.
So when you actually have a gapped theory.
Yeah. So
and
yeah.
So
yeah. Yeah. So finite real type cases, and yeah, finite real type, I think I've skipped too many things, and in these papers we give us a very concrete algorithm to start from this manifold, from this topological fundamental growth this manifold, and we give the very concrete algorithm to obtain some modular data of this TQFT.
Mm-hmm.
And from this modular data, we can determine whether it is a unitary and non-unitary. And then if this is a unitary cases, it turns out that this corresponding 3D theory, TM theory, always have a mass gap and pro to this TQFT. And this non-unitary cases, yeah, it always pro to this n equal 4 CFT and length 0.
Yeah.
Of course,
but this is this was largely based on examples, right? So my question is sort of how general is this in terms
Yeah,
of
we don't know the answer.
So for example, do you expect just with ciphered manifolds to map out all possible 3D phases or not?
Yeah, I don't know. Yeah, that's the I don't know. So
because I
as
think
mentioned,
you in your paper you looked at basically 3 fibered cases and you could get all the rank 4 up to rank 4 theories, but that's probably not true once you go to higher rank at some point. Also, you're restricting, I think, to SU2, right? To A1.
Yeah. SU.
So do you have an understanding of how that choice enters into what kind of topological phase you actually get?
Yeah, so
Changed SU3 to something more complicated.
Yeah. So for SU2 cases, so we, in a sense, that we always get some how to say, some anyons are always anyons are represented by the SU2 Wilson loop, and so this in a sense that is a how to say self conjugate, how to say is invariant on the charge conjugation. So if you consider SU2 if you construct by the topology theory using the n equal 2, then we expect that we will only get some charge conjugation invariant topological phase, something like that. But actually, there's some counterexample, some miraculous way that we get some charge conjugation non-invariant series. So for SU and SU3 cases, it automatically have some charge conjugation invariant variant theory, because that the SU3 Wilson loops are not invariant on the conjugation, complex conjugation. So we only study the n equal 2 cases. So fortunately, we get all the topological phase up to rank 4 in using that only this manifold and only the n equal 2 cases. But I think that it is just we were just lucky, and I think to generate all the topological phase, we should generalize this manifold. Maybe another class we should study this manifold, and I think that also there could be another class of the finite real 3 manifold, and also we need to study the higher rank or another type of AD type. But in this case, this analysis is much more complicated, and so
it's still kind of tantalizing, right? That you get. I mean, you might say you're lucky, but you still get everything until rank 4.
Everything rank 4 just using n equal 2 and this class of 3 manifold, and there are some more class of 3 manifold finite real. Obviously this one is not studied well. Mathematicians studied this part. And I also expect that there are some more class of this type of manifold, and also we can generalize to some higher rank or the other AD type, and interesting in this way we can also construct the non-unitary TQFTs, and I wonder that if there's some classification of non-unitary TQFTs, and how it is our construction is helpful to classify these non-unitary TQFTs. That's also often questions. And also, we only consider 3 manifold without any torus boundary, but there's also 3 manifold with a torus boundary, and which is also non-hyperbolic. Then we also expect that correspondence theory is a kind of topological theories. So then
with some additional flavor symmetry.
Maybe. So for non-hyperbolic cases, this theory corresponds to CFT with the SU2 flavor symmetry. But similarly, if we have the hyperbolic, non-hyperbolic cases, it may correspond to the topological symmetry, but there should be some effect of this boundary. And in the hyperbolic cases, this is the boundary gives some SU2 flavor symmetry in the field theory. And the topology theory, I don't know. So how this boundary will give additional structure in this TQFT. And I think we need to study that direction also.
I agree.
There
are there any other questions? because we're still recording, we could also so maybe thank Dongmin for his really nice talk again, and then I'll switch off the recording. And Jing, if you also switch off the recording.